All right. Hello, hello. People are connecting. People are checking in. And welcome, everybody. Welcome back. Week 2. And we're going to let more people come in as people are coming in. I got a fun little thing to share with you. I was messaging. I got a message from Alexandra, and she had mentioned, hey, are you going to be able to make these videos of the sessions available, referencing what I mentioned on YouTube? And she's like, I'm in Spain visiting my dad this Christmas break, and I'm 6 hours ahead. So it would really help, if you could share that when you post it on YouTube, so I don't have to stay up till 1:30 at night. And I was like, I can't believe, Alex, you're thinking about staying up to 1:30 at night. So kudos for you. But good news is you don't have to worry, Alex. When you view this, will be posted on YouTube. I did go ahead and post the first session on YouTube, and you guys will all be able to find that on my YouTube channel, Radiation Therapy Zone. And I can send an email with a link to the first video. All right, so I think everyone's here. Looks like everyone's here. So join me in welcoming Kara. Hi, Kara. How's it going?
Hi, good to see you all again. I'm good.
Good, good. So if anyone's new here, joining us for the first time, hi, my name's Lauren Brown. I'm a radiation therapist of 16 years, and I have a passion to help students pass their board exam. You've most likely joined through my newsletter and have been in communication with me regarding these sessions. We're putting on a special 2-week session with Kara Lehman, our expert RT tutor. Kara is a dosimetrist with Maryland Proton Center, and she's also a radiation therapist that continues to practice on top of her full-time commitment as a dosimetrist. She is an RT tutor, has been tutoring for 2 years, helped 7 students pass their board exams. Never has had one fail, so don't you be the first. So sorry if you've heard that before, a little cheesy, but I'm really happy that all you guys are here. I'm happy you're here, Kara. Thanks again for joining us. All right, so real quick, last week we went over things like direct proportions, inverse square, intensity, gap calculations, half value layer. Also, Kara was kind enough to share with us some practice problems. And so we're going to have an opportunity. I call tonight, the first part of tonight, BYOQ, bring your own question. And if you felt like you came up against a wall on one of the problems that we had covered in last week's session, we want to take a moment and go through where you may have gotten stuck. And don't feel singled out, don't feel stupid. We can learn, everyone can benefit from you taking the time to raise your hand and say, can you please help me understand this? And that's all it's about. It's just about seeking to understand, because as Charles Duhigg said, a problem clearly defined is a problem half solved. And so after we do BYOQ, we're going to go into new material. Kara's going to walk us through things like MU Calcs and things regarding PDD, TMR, knowing how and when to apply those. There's going to be some more great diagrams and drawings, because I know those have been super helpful. We're going to get into average life of a radioactive source, I believe, wedge and hinge angles. So buckle up. We're here for the next 90 minutes. Super excited. So Kara, before I open up to BYOQ, do you want to say anything?
I don't think so. Yeah, just definitely feel free to ask. I mean, there's no stupid question. You're probably helping someone if you ask, but thank you all for joining again. And yeah, I'm looking forward to tonight.
Okay. So let's get we had so much good participation in the chat last week. We got to get that rolling. I got to make sure you guys are with us. So everybody say, hi, Kara. How's it going? What's up? I got to make sure my chat's working. Got to make sure I see you guys. Let's see. All right. Hey, all right, Logan. Hey, y'all. Hey, hi, everyone. All right. So we got some activity. We're gonna dial this up a bit, okay? And I wanted to know how you guys did. So who type in the chat, me, if you were able to go through at least one or two practice problems. Type in me in the chat. Mike D says, hey, me. Okay, I got lots of me's. Okay, got Taylor, Maggie, Neve, Nicole, good. Me, Olivia, good. Maddie, me, good. Excellent. So who here did the ones, every one of the questions that we covered? So I think that would have been probably question 1, 2, 3, 4, 5, and 6. Who here did those questions? Did you guys type in yes in the chat? Yes, if you did them. Maddie says she got through 1 through 3, 5, and 9, had trouble with the rest. Okay, good for you, Maddie, for being able to do 5, and especially number 9, because I don't think we've covered number 9. Me, good. Okay, me, good. So it looks like people have given it a good shot, and that's the point. We're not all about homework, but we can think of it as practice, and we can use the practice to see where our limits are, our limits of understanding, our limits of actual application. And we're gonna be able to go through that tonight. So I'd love for someone to type in the chat if they had, let's see, what was your most, I'm gonna start with, where did you get stuck? Like, was there one where you just did not get the right answer? And if so, type in that number of question in the chat, and we'll go through that number. We're only going to go through numbers in which people got stuck. I don't see anybody. Chat's pretty quiet. That seems to me like people understood and were able to get the right answer. Okay, good. Maddie, thanks for piping up. Number 4, she had mentioned number 4 was given some problems, so that's okay. And then while I'm at it, while I'm writing things down, is there anyone else who had a difficult time? Maybe they arrived at the right answer, but like, if I were to ask the question differently, I would say to everybody, which one question gave you the most difficulty? Even if you were able to find the right answer, which one gave you the most difficulty? And we'll also go over that one. We will go over number 4. And I'll let those trickle in. Looks like everyone's doing pretty good. Number 4, Mike D says, okay, yeah, we'll definitely cover number 4 then. Okay. All right. So I'm going to give it away to Kara. And so Kara, if you'll help us walk through number 4. And what we'll do, guys, is I might unmute you, Maddie, if you're okay with that. And you can specifically talk to Kara directly. So I'm going to ask, you can kind of describe where you may have gotten stuck. Sorry to put you on the spot, Maddie, but so I've asked you to unmute.
That's okay. Hi. Can everyone hear me?
Yes, we can hear you.
Okay. So, I mean, I was figuring that it was a direct proportion problem. But I was just getting confused with, I think the wording was confusing me. I couldn't even really get to a point where I could like draw it out. So I just kind of skipped past that one because I was not feeling good about it.
Okay, yes, that's totally understandable. I think that the wording it uses basically the bare minimum. It kind of gives you like very little information. So it's totally understandable that it was tricky for sure. So I'll go ahead and share my screen and we can get started by going over it. Can everyone see that? Okay. Awesome. Okay, so this is the problem here. So it says, what would the field size be? Here, hold on 1 second. It says, what would the field size measure at the skin surface for a patient who is treated isocentrically APPA to midplane with a separation measuring 20 if the field size measures 15 by 19 at the isocenter? So I can just start by drawing that picture kind of in the gray like margin, just kind of like I did last week, and see if that helps to make sense. But the wording is definitely tricky and it's hard to even kind of get a picture to come to mind. But if we just start with, drawing our patient, so kind of just draw a circle here, and then it says APPA. So you might think in your head, oh, I need to worry about, two beams, one coming in from the AP, one coming in from the PA. But in this problem, because it's saying that it's mid-plane, you can just go ahead and whatever you calculate for the AP is what you'll calculate for the PA as well. So you'll get the same answer regardless. But for example, like if it would say the isocenter measures 5 centimeters deep from the AP and 15 centimeters deep from the PA, you're going to get a different answer. Then it might just be asking for you to solve for one, like just for the AP or just for the PA. And then you have to kind of be careful that you're keeping it straight and that you're solving for the right one. But for this case, which I feel like the boards kind of ask, they kind of do a lot of like mid-plane, like mid-separation. So I feel like this is kind of a good one to be able to know. But if we just kind of put our isocenter here, like a little X here in the very center of the patient, kind of like designating that the isocenter's right in the middle of the body, right, like exactly mid-plane, you can kind of just calculate for like the AP. So again, it doesn't give us very much information, right? Because you'll want to find your distance from the source to the isocenter, and you'll want to find your distance from the source to the skin. But it doesn't really tell us. So for one thing, if it doesn't tell you the distance from the source to the isocenter, you can kind of always assume 100. That's kind of what the boards want you to do. If it doesn't tell you, you can assume 100 because that's what it normally is at most clinics. But of course, it would have to tell you if it's something different, if it's like 105 or 90 or something like that. So we can go ahead and just say the distance from the source to the isocenter is 100. And this is just that same little scale that I used last week, kind of just drawing from the top, from the source down to the isocenter and just designating the distance in that way. And then on this side, I'll draw the distance from the source to the skin. But right, again, the problem doesn't tell us the distance from the source to the skin. But what it does tell us is that the patient separation is 20. So I'll draw a little scale here, kind of like overlapping with that skin surface from the AP to the skin surface from the PA, and just put a little 20 here. So then you can kind of start to see, okay, so if the patient measures 20 from the AP to the PA, then from the isocenter up to the AP, it has to be 10. And from the isocenter to the PA, it has to be 10, right? Because if you add 10 plus 10, you get 20. So like I'll draw a little scale again over here, just saying from the isocenter to the AP, it's 10. From the isocenter to the PA, it's 10. So again, that doesn't really help us or tell us much, but it is getting us closer to helping us figure out a distance from the source to the skin, because we know if the distance, and I'm just going to switch the color here to make it a little bit easier so I don't like what I overlap kind of you can see. But if we know that the distance here from the source to the isocenter is 100, and then from the same point, the isocenter up to the skin surface is 10, we can just do 100 minus 10 equals 90, and that will be the distance from the source to the skin surface over here on this side. So I can now put a 90, and that's the piece of information that we were looking for our direct proportion. And then the problem tells us our field size at the isocenter. So going across here, it's 15 by 19. So I'll do 15 by 19. And then the question mark is this field size up here that we're looking for. So it wants the field size at the skin surface. So I'll just put a question mark. And again, like we kind of talked about last week, because of divergence, we know that the answer should be less than 15 by 19, right? Because down here, the field size is wider across the patient. And up here at the skin surface, it's going to be smaller. So at this point, we can go ahead and we can plug in our direct proportion. This will be one that we want to calculate twice because the answer is asking for the length and the width of the field size. So we'll do the problem once using 15 as the one width of the field size, and then we'll use 9 as the length. So I'll go ahead and just set it up like we did last week, kind of just doing x1 over x2 equals y1 and y2. And this is the part that can get a little tricky to just make sure that you're putting the right numbers in the right spot. But again, you just want to designate what's going to be the x's. Is it going to be your field size or is it going to be your distances? It doesn't matter which one you pick. You just want to keep them consistent. And then you just want to put across from that. If your x1 is your distance to the isocenter, you want to use y1 as your field width at the isocenter. So for x1, if we say that we're going to use x's as our distances, we can put 100 as the distance for x1 over 90 as the distance for x2, because those are our two distances from our source to our isocenter and then our source to our skin. And then for y1, we just want to use, because 100 is the distance to the isocenter, we want to use 15 as the field size at the isocenter. And then we'll leave y2 as the variable that we're searching for, because that's the field size at the skin surface, which corresponds with the distance of 90. So then if we do our cross multiplication, we would have 100 times y2, equals 15 times 90. And then to get y2 by itself, we want to divide by 100. We want to do that to both sides. This side will cancel out. And we're left with y2 equals, then if you do 15 times 90, you should get 1350 over 100. And then if you divide that out, you're left with 13.5 for the first field width. And then of course you just want to do the same thing. This part gets a little bit simpler. Again, I recommend, if you're on your board exam, you don't necessarily need to write out this everything again, but you could just substitute anywhere that there was a 15, you would just put the 9 in, because you're now using the field length. So then 100 over 90 equals, instead of 15 for y1, you'll use 9. And again, solve for y2. And then simply to kind of like make the steps a little bit shorter here, you'll just do 9 times 90 divided by 100. Same steps that we did on the left-hand side. And then that answer, if you multiply 9 by 90 and divide it by 100, you get 8.1. So then the answer for this would be A, where it's 13.5 by 8.1. Does anyone have any questions, or did any step of that kind of get confusing or didn't really make sense?
So I'm looking at the chat and I don't see anybody typing anything. If you understand it, can you say understood in the chat? If that explanation was good. Otherwise, we can go through it. Maddie says that makes a lot of sense. Mike asks, does the answer of the field size should it be smaller than the field size given? Okay. So do you understand, Kara, what he's asking? I think he's asking, should your answer for the field size be smaller than the field size that is given?
Yes. So if he's meaning the 15:9 at the isocenter, the answer at the skin surface should be smaller than 15:9 because we know that the field is wider at the isocenter than it is at the skin surface.
And that's due to divergence, correct?
Yes, exactly.
Okay. Yep. So we got Taylor understood, got it. Brooke understood. Nicole got it. Olivia understood. Neve understood. Yep. Great. Mike says thank you. Excellent. So Olivia brought up a good point before we dove into this question number 4, which I'm glad we went through it, because I learned something with this question. It's that, you know, questions on the board may not always give you really tidy numbers to plug into your direct proportion formulas. So Kara kind of was a little tricky, you could say, because she didn't give you the SSD. You had to like find the SSD before you could even start plugging in numbers. And so being able to recognize that was something that I learned. So thank you, Kara. But Olivia brought up a good point with, Kara, would you be able to just take a brief minute to just go over the correct answers? Not like problem by problem and work them out, but I mean, like just real quick, like maybe 1 through 6, like what should the answer for number 1 be? That way, because I didn't think of this, but she asked for an answer key. You know, do we have an answer key for these practice problems?
Yeah, no, definitely. That's good because yeah, I didn't think about that either. You probably don't know if you really have a question until you know the answer. So yeah, going over 1 through 6 really quick. 1 should be answer B, where the answer is 165 centigrade. 2 should be D, where the answer is 1.24. 3 should be C, where the answer is 130. 4, like we just said, should be A. And then 5 should be B, where the answer is 0.182. And 6 should be A, where it's 0.0072. And then I know some of you might have attempted 8 and 9, which are intensity questions that we did do last week. However, they're a little bit tricky, but I can go ahead and just give you the answers so that you know if you got it right or not, but both of them are C. So for 8, it's C, where the answer is 6.25, and then 9 is C, where it's 356.
Okay, great. So now a question for you guys is seeing the answers, if you have your practice problems in front of you, now I can ask you, you can give a good answer, but like, did any of you guys get something wrong? If so, maybe we can go over it. So if you did get something wrong, put that number in the chat, please. Chat's pretty quiet. It's like maybe everyone got them right. And then I think I missed number 7. Kara, are we going to go over a problem like number 7 later today?
Yes, we are. So it's activity, which is it's very similar to intensity, but we did not cover that yet.
Great. Okay. Well, I don't see anyone in the chat. Oh, here we go. All right. Olivia says she did complete all 14. Way to go, Olivia. Would you be able to mention those as well? Before she mentions those as well, all right. Maddie says, can we go over 6? Yes, great. Before she mentions all those answer keys, I actually, since we're going to go over new material today, some of those questions that she did not give answers to pertain to the new material. So I'd like to give people an opportunity, the people that didn't go through all of the 14 questions, those people an opportunity to solve those without answers. And then I can just send an email with the answer key, and people can open the answer key email at their own when they're ready. So Kara, looks like Maddie says, can we go over number 6?
Okay, yeah, sounds good. I'll just
So
go ahead and erase the board.
sorry to interrupt, Kara. Anyone want to take pictures of this? Feel free to do that now. And she's about to erase this and move on to number 6.
Okay. All right. So
Maybe we can go and ask Maddie again. I'll ask Maddie to unmute herself. Is there a specific question you have about number 6, Maddie?
Nothing really specific. I just felt like I needed some help through it.
Great. Okay, we'll go over it. Thank you.
Yep, no, definitely makes sense. For this one, this, can kind of be confusing just looking at it, but the formula for decay constant is, I'll just write it out here. It is the lambda equals 0.693 divided by the half-life. That's a 3. Divided by the half-life. And so what you can do in order to solve for it is just do your decay constant, which is the lambda equals 0.693, and then divide it by 96. And then that should give you an answer of A, which is 0.0072. So any questions on that?
Okay, Maddie says, thanks, much simpler. It was making much simpler than I was making it in my head.
Yeah, no, the word this problem does look very complicated. But fortunately there is just a simple formula for decay constant.
So maybe the trick is recognizing when you need to work the formula, because it's obvious when you have the formula in front of you and it's just 0.693 over the half-life. And then you can just see that, oh, all I have to do is plug in the half-life. But to me, I don't really connect lambda with the decay constant. So I guess I might be a little nervous that if they just gave me the decay constant, if I would plug it in the right place. And then how would I recognize that I need to use this formula? Is this formula only used with half-life, or are there other formulas with half-life?
Yep, so the only one that's similar to this, right, is whenever they're asking for the linear attenuation coefficient, which I think we went over last week. Let me pull it up here. But that's where we use the mu, right, and half value layer instead of lambda and half-life. So something that could be very similar is this question, instead of decay constant, could ask for the linear attenuation coefficient. And instead of the half-life being given, it could give a half value layer. And then you would use the same formula. I'll just write it here on the right-hand side where it's mu equals 0.693 divided by the half value layer. And we kind of talked about that last week, how it can kind of be rearranged where they could ask for the half value layer and give you the linear attenuation coefficient. Just like this one, it could give you the decay constant of the radioactive material and ask you to find the half-life. So then it will kind of make sense as we do activity problems, because just like the intensity problems, right, where I'm just going to write it here so you can visually see it. We discussed this formula last week where we did I equals IO and then times E raised to the negative, and then we did mu times T, which is, right, the linear attenuation coefficient times the thickness. But over here under lambda, I'll write the activity formula that we'll kind of do here in a minute, where it's A equals A0 times E raised to the negative, and instead of mu, it's actually lambda. And then instead of the thickness, where it's T, it's actually T, but it's time. So it's like a length of time. So it'll kind of make sense whenever you see a formula, but it'll be something like the initial activity of cobalt-60 was this. what is the activity after 17 years? And right, that's a unit of time. Or it might say 2 days or something like that. So anything that's like minutes, seconds, days, years, that would be a unit of time. So you can kind of see how these formulas right here are very similar, but one deals with the decay constant, which is activity, and the other deals with the linear attenuation coefficient. But just like intensity that we did last week, where like here for the mu, it normally doesn't like tell you the linear attenuation coefficient, it'll give you the half-life. And then that's when you need to plug in 0.693 divided by the half value layer. The same goes for activity, where I'll just draw an arrow to the lambda. It won't normally give you the decay constant, but again, for this, you'll have to basically plug in this formula that we just did, and it'll give you the half-life. So then you'll have to do 0.693, again, this exact problem that we just did, divided by the half-life. So see how you can kind of, this is like a very basic step. This is like step number 1, you could say, of like the most basic question of solving for the decay constant. But you would be like very lucky to get this question on your boards. But a more common question is you would probably get an intensity or an activity problem where you might know the formula, you might know that you need to figure out the decay constant, but the problem doesn't give you the decay constant. The problem, like this problem, gives you the half-life, and you have to solve for the decay constant by memorizing the formula 0.693 over the half-life if it's activity, or 0.693 divided by the half value layer if it's intensity. So does that kind of make sense to everyone? These can kind of get a little confusing, but it's always kind of easier to see side by side. But definitely let me know if you have any questions and I can explain it further.
And Kara, so we're going to cover activity later today. We're going to walk through it together, correct?
Yes. Yep, exactly.
So if anyone is like, where did you get A equals A naught with E exponent to lambda times time? If anyone's like, where did you get that from? We're going to go over that later today. And so, Kara, is it that there's really kind of like activity and intensity equations? It's the two circled ones at the bottom. It's really this one here, which is activity, and this one here, which is intensity. Those are commonly seen on the board. And help me understand, like, basically there's components to this equation that basically number 6 is a component to that equation. So number 6 is kind of like, it's like a primer or a first step, like you mentioned, to actually being able to solve one of these questions. For instance, maybe the board gives you an activity question, and number 6 is important to know because you might need to solve for lambda before you can actually solve for activity. Is that right?
Exactly. Everything that you just said is exactly correct. 9 times out of 10, they probably won't give you the decay constant because they like to do this on the boards where they try to work in as many formulas into one problem as possible because, right, they only ask you 200, but they don't have room to ask for every single formula. So sometimes I will say I've seen this on Mosby's questions, like when you're practicing for the boards and you're doing like the online questions. This is a question. I don't think I even made this one up in my head. So I think maybe they think that you could possibly get something like this on the boards, which would be like super nice. But kind of like Lauren was saying, 9 times out of 10, I think that this kind of question, this formula, the lambda equals 0.693 over the half-life, is worked into activity. And same with the linear attenuation coefficient and half value layer.
Okay. So, oops, I'm still. Thank you for explaining that a little in more detail, Karen. Thank you, Maddie, for asking, because As you can see, it's just the first step to something a little bit more in depth that we'll cover later today. But Maddie, before we move on to the new material, do you want to ask anything while we're on this topic? Feel free to type it in the chat, or any other student for that matter. If while we're on this particular topic, do you want to type in anything in the chat? Okay. Oh, Maddie says, thanks, much simpler than I was making it in my head. Maybe that was an old one. And she said, Maddie says, no, that makes sense. Okay, great. All right, so great, we're gonna move on. And so we've given all the answers out. I think, gonna make sure, I think we just wanted to go over number 6. So I think we're ready for new material. Does that sound good, everybody? Say yes in the chat. You want to move on to some new material? Well, chat's sleepy. No one's saying anything. All right, guys. So wakey, wakey. Oh, here we go. Maybe my chat, maybe my chat's not updating. But yeah, okay, great. I see someone said bring it on. Okay, Logan, we're gonna bring it on. Maddie says yes, Maggie says yes, Mike D, yes. Okay, everyone's ready. Excellent. I'll be quiet. It's all you. Take the stage, Kara.
Okay, awesome. The new material that I have next in line is activity. So this is kind of, where we got to leave off last time, because we kind of hit our time mark where we stopped with intensity. But next, and I think equally as important, because again, like I said last week, we're kind of going in order of, I don't like to say the word importance, but just how much I think it comes up on the boards and how good it is to have these formulas memorized. Just because, it might come up a few times, and if you don't know it, you might get more than one question wrong. So this is a good segue into it. So if anyone wants to take any pictures of this right here, feel free to do so, and I will erase the board in a second. But these are really nice. These formulas that I have circled at the bottom are just really nice to have memorized in your mind, and then to, add that to the list that you'll jot down at the top of your whiteboard or whatever as soon as you walk in to take the boards, because otherwise you can get really confused and you can say, oh, which one had the linear attenuation coefficient and which one had the lambda with the decay constant. And if you just kind of, keep these two straight, I feel like it just makes things a lot simpler. And then of course, if you get a simpler question, asking for the decay constant, you can be like, okay, I know that relates to half-life, because they could give you, calculate the decay constant, and they could give you the half-life and the half-value layer, right? And that would mean that the half-value layer is not of importance in this problem. If it's asking for the decay constant, you want to use the half-life. So you want to make sure, that you have your formulas memorized and you have it straight, that the decay constant relates with the half-life and the linear attenuation coefficient relates with the half-value layer. So I will erase the board here, and I'm going to stop sharing my screen, and I'm going to switch back to the material that we were going over last week. Just give me 1 second to share the right thing. All right, so everyone should be able to see that, but this is where we left off. So like I said, we left off with activity right after we did the intensity. So again, starting with this question, a very similar formula with the intensity, but I'll go ahead and I'll write it out here at the top. So it's A equals A0 times E. So we're still dealing with this exponent that I know we kind of dealt with last week. So, depending on what calculator you have, hopefully you kind of have it squared away how you can plug in the E, but if not, we'll work through it together. But this problem says find the activity of a source after 70 hours if the initial activity was 100 Curie and the half-life of the source is 25 days. So this is what a typical activity problem looks like, right? It gives you an initial activity. So, right, that's your A0. And then it gives you two kind of units with time. So the one is your half-life, right? Like I said, they're typically not that nice and just give you the decay constant, which is the lambda in this problem. It's going to want you to solve using the 0.693 divided by the half-life and find that decay constant. And then times time. Like we said, with intensity, the T stood for thickness. So it was the thickness of the material, like in centimeters or meters, but this T stands for time. So if I'll go ahead and I'll plug in, what we know and what we're searching for. So in this problem, we're searching for the new activity. So the problem's already set up correctly in order. So A equals, and then for A0, we'll put in 100 Curie times E raised to, and then because it doesn't give us the decay constant, we'll go ahead and do 0.693 divided by, and then I'll just put the half-life because remember that's the mini formula inside this longer formula, and then times the time. I'll just put that for now. So then on the next line, if we're to write this over again, 100 Curie times E raised to the negative 0.693, and then we can plug in what we know. So the half-life, it says, is 25 days. And then times the time, because it's saying the activity of a source after 70 hours. So we'll put in 70 hours here. So the only thing I would caution to be careful of is first making sure, because both units are time, you want to put the half-life in the right half-life area of the formula under the 0.693, and the time, times time, because otherwise you'll calculate the wrong answer, and more than likely it'll be an answer that the board gives you, but it won't be the correct one. So make sure, you see 2 units of time, but it's important to get that in the right spot. So make sure you put the half-life under the 0.693. And then the other tricky part that is often they throw in one of these problems on the board somehow is they'll switch the units on you. So in this case, the half-life is in days and the time is in hours. So you want to just make sure you're really careful of that, because again, they'll probably have an answer that if you were to multiply this out as it is right now, it's probably one of the options, but it's probably not the correct answer. So it doesn't matter if you convert the hours into days or the days into hours, it totally doesn't matter either way. You're going to get the same answer, but you just have to have the units match in order for them to cancel. Because, right, you see that your answers are in Curie, so you need your times to cancel out. And you have, a time here in hours at the top and a time here in days at the bottom. So it's going to cancel once you multiply, but you just have to have them matching. So again, it doesn't matter. For me, whenever I calculated this problem, went ahead and I changed the hours into days. But whatever's simpler for you, I don't think one way is easier than the other. I just picked one and kind of went with it. So I'll just on the left-hand side here, kind of like work out how I did this and do a quick refresher of like unit multipliers and at least how I was taught. But of course, if there's another way that you guys know that makes sense in your own head of how to, get units matching, definitely stick to that. This is not meant to confuse anyone, but I'll write in the gray area where I normally draw the pictures. But I just kind of always start it by X equals, and then if you do 70 hours times, and then this is where I kind of add in that unit multiplier, where if you have hours on the top up here, I'll put hours on the bottom down here, and then change it to what we're searching for up here, so days. So that way your hours will cancel out. And then on the right-hand side here, you'll need to just put in how many hours are in one day. So in this case, you'll put 24 down here and 1 up here. So then simply when you go to multiply this, you'll do 70 and you'll just divide it by 24 and you get 2.92. And again, that's in days, which is important. because now whenever we do our next line here of the activity problem, we'll do 100 curie times E raised to the negative 0.693. And then because we now converted our 70 hours into days, we'll keep the 25 days here at the bottom. And I'll just keep the unit with it to kind of show how this works. And then times 2.92 days up here. And now whenever we multiply this out, our days will cancel. So I'm just kind of crossing out the unit days here. And we'll be left with our answer in curie. So you can see how you would get a totally different answer if you multiplied, the problem by 70 at the end versus 2.92. So you just want to make sure that you are just aware of your units and that they cancel out. So next, kind of just working through the next step here, if you just still do 100 curie, because like I kind of mentioned with the intensity problems last week, I feel like it's easier if you kind of, start with the right-hand side of this problem and kind of before you even plug in the E, I would just recommend going ahead and in your calculator doing 0.693, dividing that by 25, and then multiplying that by 2.92. And you would get an answer of E to the negative 0.08085. And I'm just being extreme, taking it to a lot of decimal places. Even if you did 2 or 3, it would probably be fine. But just for the purposes of teaching, I'll just definitely show you what the exact answer I got. And then now if you're to plug it in your calculator, which this is the tricky part, so definitely let me know if anyone has any problems plugging this in, but you should just be able to do 100 and then times E and then raise to, which normally when you plug an E in your calculator, it already knows you have to raise it, but make sure you keep the negative sign and then do negative 0.08085, and you should get an answer of 92.23 curie. So I'll give everyone a minute to try to calculate that. But the only thing I'll say in the meantime is that this kind of makes sense because you want an answer that's less than 100, because if that's your initial activity and we're decaying, we should be going down, right? You don't have, you don't have sources that go up in activity whenever they're decaying and they have a half-life. So this is just slightly lower than the initial activity, but it kind of makes sense, right? Because the half-life is 25 days. So that's a fair amount of time. And when we converted our hours into days, we really only have about 3 days that passed. So if the half-life's 25 days, where your activity is going to go from 100 to 50, and you only have 3 days, or to be exact, 2.92, you're like, oh, okay, it should just be like a little bit less than 100. So like the answer A, where it's 14 curies, that's very crazy. D is obviously not right since it's larger than 100. So you're kind of down between B and C if you're to think about it like logically. And then whenever you work it out, you should get C as an answer. So does anyone have any questions about that? I know these are not that simple, just like the intensity. They're kind of a lot. So definitely feel free to ask if anyone has any questions.
Yeah, I really like how you went through logically how to look for something that would be approximate to the right answer. Like you'd mentioned, when you compare apples to apples and you've converted that 70 hours into days, you realize it's almost 3 days, which is, 3 days is not close to the half-life. So we wouldn't expect it to be anywhere near half of 100 curies. We would expect it to be somewhat close to 100 curies because, what's 3 days in the scheme of 25 days? We do have a couple questions coming in, so let's see what they say. So Logan says, when I multiply 0.693 divided by 25 and multiply 2.9, I get 0.08094, which, and so I think what Logan is doing is, he clarified and he said divide. So I think he meant to say when I divide 0.693 divided by 25, and then multiply 2.9, I get 0.08094. And so I guess what he's saying is he did not get 0.08085 like you did. Era, do you want me to get Logan to be able to talk it out with you, or do you see what he's talking about? Maybe an error he made.
Yep, no, I completely understand what he's saying. So thank you for bringing this up. Whenever I typed that in and did what you said in the chat, I got the same thing, 0.080 and then like 94, I think it was. However, the only reason why I got this, and maybe this is a downfall of like trying to be too exact, but I used the full number from dividing 70, or yeah, I should say 70 divided by 24 whenever you look at the formula on the left-hand side where I was solving for days. So instead of using 2.92, I used that full answer. I actually stored it in my calculator. And that's why I got a slightly different decimal to like the thousandth place. So that's why it's slightly different. But thank you for pointing that out. Again, in the grand scheme of things, it shouldn't really give you a very different answer, but that's just to explain how I got my answer versus yours. That's why.
So I'm kind of curious. I want to work it out his way and see what answer he gets. So I'm going to type it in my calculator, or maybe Logan, you can just type in the chat. What answer did you get? Oh, and he said I did the same thing. Okay. So maybe he got the same answer.
I was going to say when I worked it out, I got 92.22. So yeah, a slight difference. Yeah, instead of 0.23, I think you would get 0.22.
Okay. I did the same thing. Okay. Now he's getting something completely different. Oh, but let's see. So what he's saying is, now I can only get 0.080388. And then he said, which one is right? Was that a question, Logan? You want to know which one is right, if it's the 0.080388 or if it's the one.
Hey, Lauren.
Hey, good. Thank you for unmuting yourself.
I'm on an iPad, man. It's really tough to type.
Yeah.
No, I was getting the 0.08094, but now I'm getting the right one.
Oh, I got you. So you're on the right page.
Yeah.
Yeah. I did go ahead and type in your initial results into the complete equation, and I got 92.23.
Okay.
Is the right answer. So I think.
So yeah. Okay.
Either way you do
I
it,
appreciate it. Yeah.
just off by like a very small number.
Okay. I appreciate you guys.
Yeah, you're welcome. Thanks for jumping on. Okay. So I think we're good with that. You know, I understand sometimes actually typing in these functions because they're just unusual functions. Like, how do you really type in all this mumbo jumbo into your calculator? So what I might do is just make a quick little screen share and share it on my YouTube, and how I type in this equation into a scientific calculator. That may or may not help you guys. Type in the chat just so I know if I made like a quick little screen share and put it on YouTube. Would that interest you? You could type in yes, or you could just not say anything. Okay, Logan said yeah. Okay. The more yeses I get, the more likely I'll do it. But looks like everyone's pretty good. But I'll go ahead and do it. It's definitely worth it, because it is a little funky. And if you're on an iPad, I know I'm on an Android phone, and I had to do a different order of operations just so I don't make the same mistake as I did last time, because I know it was a challenge for me and Logan last time. All right, well, I'm done talking. I'll let you take it back over, Kara.
Okay, sounds good. If anyone wants to take a quick picture of this, feel free. Otherwise, yeah, the answer is C for this one. I'll go ahead and clear it. So now moving on, I just have one more type of activity problem that, again, I think we can go through kind of quickly. We don't need to, spend forever on it, but the only thing I just want to highlight is in this problem, which I know this came, there's a very similar question like this on the Mosby's, which I use to reference a lot because that's how I studied for my boards. And then I have a lot of students that use that. And it's kind of nice because they have like 200 questions that you can kind of pretend like is the board exam. So I know a very similar question is on there like this, and that makes me think that they could ask this on the boards as well. But this type of activity problem is the same in terms of you'll use your same activity formula. So I'll go ahead and I'll write it here. But you just have A equals A0, and then e to the lambda t. But in this case, if you read the problem, it says there are 168 millicuries of cobalt-60 today. How much activity was present 8 years ago? So if you kind of break this down, you can see that it's actually, in this case, you're solving for A0 and you're given A because it's saying that there's 168 millicuries today. How much is basically it's saying is the initial activity. So in this case, and like in school, I've helped students that are currently in school, your teacher wants you to know like how to, derive this equation and use like the natural log to get the E kind of away so that you can get A0 by itself, which is very complicated and very time consuming. And I do not think anyone has time on the boards to be writing this out on a whiteboard. So I just want to share with you this little trick that if you ever get an activity problem where you're searching for A0 and you're given A, it's a lot simpler than what you might think you have to do. So if I were to write this out and fill this out with the parts that we know, it would be, 168 over here, 168, and then you're searching for A0, so we'll leave that as our variable, times E raised to, and then we know this is 0.693 because again, they didn't just give us the decay constant, they gave us really not much information at all. But this would be another way that the boards would work in things that they want you to know, right? So you know that you have to memorize your half-lives. This doesn't even tell you the half-life. It wants you to use the knowledge that you should have memorized for the boards and just know what the half-life of cobalt-60 is. So whenever you study for your boards, there's just a few isotopes that they want you to know the half-lives for, but cobalt-60 is one of them. And then I'll just put the time here to finish the formula. But in this case, again, I'll just, keep going with writing this formula out where we're still solving for A0 and then E to the negative. So in this case, and again, people might use like slightly different things that they memorized for the half-life of cobalt-60. In this case, I'll just use 5.23. Some people, I think, memorize 5.24 or, different things. And this is in years. But again, you should get a very similar answer no matter what you use. And then the time that it gives you in this problem is 8 years. So the good news is with this problem, our units equal, right? We have years and years. So no need to do a unit multiplier because these units will cancel out. But again, if you're to solve this, because right now you have all your numbers in, you have your 168, you have your half-life of 5.23 years, and you have your time in 8 years, you're still like, wait, this is a very complicated problem to get A by itself. You can't just simply divide both sides by E. If you try to type it in, I don't think your calculator will give it to you, or it will just give you some kind of crazy answer. But I just want to share this very simple thing that is very shocking to, I feel like, a lot of people, and I don't think that they teach you in therapy school because they want you to know how to, use the natural log, which is, good and fair and definitely should be taught in school. But on your boards, what you can actually do for this type of problem is switch it and go back to solving for A. So I'm just continuing writing the formula. A equals, and then in this case, we're going to use the 168 for A0. And you might be saying, it's not A0. Why are you plugging it in for A0? This feels wrong. And it kind of does, but it's going to work. And then go ahead and just keep going across the formula and do E raised to. And then in this case this is where the formula works out, but you actually just don't use a negative. So like, see how it's E raised to the negative 0.693? You actually just raise it to nothing, just a positive number. So you'll take out the negative and do 0.693 divided by 5.23. And I'll just leave out the units for now because we know that, the years cancel, no need to do any extra work. And then if you plug in this number, so again, I would recommend doing the step where you multiply 0.693, take that number, divide it by 5.23, and then multiply it by 8. So if I'm to do that now, times 8, you should get 1.06. Just to keep it short, because the next two numbers are 0, 0. I'll write out that next step. E raised to, and then I'll just put it in parentheses, but 1.06. You just plug in, if you now put in your calculator 168 times E raised to the 1.06, remember, don't put in the negative like you normally do for any activity problem, you will get the answer. So it's actually, in my head, like even simpler in terms of you just skip the step of taking out the negative. So it's really crazy. It's this big, long physics explanation as to why this works, but basically because you're switching it and you're searching for activity years ago, you don't need the negative, which is, how they came up with this formula, because your activity is smaller than your initial activity. That's why it's raised to E to the negative. But now that you're switching it and you're actually solving for activity instead of initial activity, it's raised to E to the positive number. And you would get an answer, if you were to calculate this out, of 482, which is B. So does anyone have any questions on that? Again, I can't even explain to you like the reasoning as to why this works. All I know is I share this with every student that I've tutored because all of them have presented this question to me and they're like, I have no idea how to solve for the initial activity. And only one time with a student, we had to do it with the natural logs in order for a homework assignment for actual class. And it's very complicated and it's not fun, but I can certainly do it if anyone needs to know it. But like I said, for the boards, I would 100% just recommend this way of just taking out the negative.
Okay. So, any comments? Feel free to type them in the chat. So it's basically, Kara shared with us a little shorthand for circumnavigating the long form log calculation to try to get A naught on the side of the equation by itself. So she basically has a cheat that works out by essentially flipping A with A naught and then not having the negative in the parentheses with the log. Did I understand that right, Kara?
Yep, exactly like what you said. It's pretty much exactly what is happening. You plug in 168 for the A naught, which feels wrong because you know that that's not where it goes in the equation. But if you take out the negative, the E raised to the negative, you'll get the right answer.
Okay. Just so no one else feels bad. I did not get the right answer. I don't know what I did wrong.
Okay.
But I got 484.91 millicurie. It's very close, but it's different. Not exactly sure.
Okay, I think you're right on that because I even have on my paper like 4.84, which I mean yours is rounded up to 5, so I don't even really know how I got this initial answer of 4.82. I probably again stored something somehow, but yes, I think that you're right by like 484 point whatever you got. Yeah.
So you could round it up to 45, but
Yeah.
okay, we got some people contributing. Let's see, we have Logan, that was a great tip. Neve, I got that too when I used the half-life 5.23, but when you used 5.26, the half-life, then you get 42. Oh, thank you, Neve. So
Okay. Thank
when
you.
you use a different half-life number, you know, it's marginally different. You know, it's up high in the order of operations, but you move lower and lower, it has a greater impact on the answer. To the degree of, it looks like three millicuries. Olivia says or asks, would this have to do with would this have to do with half-life? I'm used to using 5.26 years for cobalt 60. Okay, so again, this is kind of like what Kara had mentioned, like maybe some programs have taught 5.23 half-life for millicurie or half-life for cobalt 60, and maybe some programs are teaching 5.26. Is that about what your understanding is, Kara?
Yeah, I'm actually glad that this came up. And it's funny that, I did this myself and somehow got, one using 5.26 and one using 5.23. But this is a great example of how the boards will be because you'll be like, I know I'm memorized, this certain number for half-life. It's in this textbook, it's in this textbook, it's in this textbook. How is none of the answers on the boards like, and you'll get something pretty close, right? Like 4.85 instead or 485 instead of 482. But you're like, how did the boards calculate this? Like, what number were they possibly using? But it happens all the time. You'll see it on the boards, where they might have used a slightly different number. So if you get something pretty close, and it makes sense to you, like in terms of, right, like, the number shouldn't be smaller than 168, right? So we can eliminate A and like things like that. I would say that you're probably like pretty safe. They like to use, or I shouldn't say like, I don't know how they come up with what they use for things that they think you should have memorized, but it might be slightly different than what you used. So yes, definitely you get something similar. It's like within a small number, it's probably right.
Okay, so what I'm hearing you say is basically, if you arrive at an answer of 485 millicuries on the board exam with a question like this, and you're given those 4 answers to select from, it's not like 2 of them are very similar in this example. They're all very unique, and so it would be good to choose the one closest to your answer. If you've logically thought out your answer, maybe you've gone through it one more time, you've maybe gone through the calculation again to make sure you didn't put a number in the wrong place. So in other words, you're confident of your answer is 485. And then you would say, Kara, that it's safe to select the answer that's closest to the answer that you arrived at. Is that right?
Yep. Yeah, that's a great way of saying it. In my head, like what I've noticed from questions that I, see from students and what I know about the boards is they aren't going to be that picky because it's really not that important to know down to the 100th, the exact half-life of cobalt-60. That's really never going to benefit you that drastically in the world of radiation therapy, but they'll just be really happy that you knew from just this information that you needed the half-life of cobalt-60 and that you were able to come up with, 5.2 something, because that's already like pretty difficult to do. So they'll be happier that you did that, and they shouldn't give you, answers that close together for questions like this, because they know that there's some variability in what you might have memorized from different programs around. So shouldn't be anything that exact. If there is, like if there was an answer of 482 and 485, you would just go with what you have memorized. Like there's nothing that's like a pretty unfair question in my opinion. And I haven't seen anything like that unfair, because again, they're just happy that you memorized a fairly close half-life, and knew that you had to apply it in this problem, because that's already pretty difficult to do from just getting this question. So that's what I've noticed, from my experience.
Okay, thanks. And before we move on, are you able to comment on particular isotopes where it's important that you memorize the half-life of?
Sure, yeah. I feel like there's a list of about 5 or 6 maybe for the therapy boards, but like I know iridium 192 is one, because I mean, if you just think of anything that you've really even seen in the clinic, that's, used for HDR brachytherapy a lot. Like gold is used, palladium, like 103, those are, used for seed implants. And now they use, it's escaping me. I think it starts with an I. Is it iodine 125 for seed implants? Like those, I just stick to, what is actually used in radiation therapy. So anything for HDR, LDR, and then your cobalt-60, which again, no one really uses like a cobalt-60 linac, but they'll still want you to know that these days. And other than that, that's pretty much the list.
Okay, thank you.
Sure.
So I know we're getting close on time. So how many more do we have? Are we getting close to getting there? I think, do we have monitor unit calculations and maybe hinge and wedge angle?
Yep. Yeah. So next we have just 2 monitor unit calculations, and then hinge angle, wedge angle, and average life, which those last 3 are pretty simple. I don't have anything, earth-shattering to say. All of you probably have learned that in your therapy programs. Average life is very simple, but I just throw it on there to make sure that people, because I don't like anything coming up like a week before the test where students are like, I totally forgot about wedge angle and hinge angle. I totally don't know that formula, and I would have blanked on it on the board exam. So I just always throw in a problem just to make sure you have that formula memorized. But if we don't even get to that, that would like not be the end of the world. I'm sure you all know how to do it, but the monitor unit calculations are the big one I know a lot of people always ask about.
Okay, so we're ready to move on, I think.
Okay, yeah, if no one has any other questions, go ahead and take a picture of the work here if you want, and I will clear the board, and then we'll head right into monitor unit calculations, which should be next. Okay, so I'll just get started here. I don't have too much to say. A lot is just done by working them out. Again, I feel like I've mentioned before, monitor unit calculations are a really great thing that the board likes to throw in, different things that they want you to know. maybe they'll give you a dose in gray and they'll want you to convert it to centigrade, right? Because you'll have a calibration factor that goes on the bottom of the MU calculation that's in centigrade per MU. So you want to make sure that those units cancel out. You're just probably not going to get a question on the board as simple as what's 30 gray into centigrade, right? That's something that would be worked into another problem. So we can kind of work through this and I'll, point out some of the things that are smaller formulas or smaller things to know inside this MU calc. But a lot of times I know a lot of people have the questions of, am I going to be given a graph? That's a lot of things that oftentimes are tricky about MU calculations, right? Because you have this huge graph, you have one for 6 MV, 10 MV, 18 MV, you have your different field sizes, you have your different depths, you have PDD and TMR, and you're just like, how do I know which one to use? The good thing on the boards is, they don't have room to give you all these graphs, but they'll often give you more information than what you need to know. So that's what I would just say going into this. They might give you PDD and TMR, and you want to know that you only need one of them, depending on if it's an SSD treatment or if it's an SAD treatment. So the one thing I'll just say before even attempting this problem is that you want to know that PDD equals non-isocentric or SSD. And by equals, I mean, all these words are interchangeable. So if you would see in your problem, it's saying this is a non-isocentric setup, or this is the SSD for this patient is, whatever. That's when you want to use PDD. And then in contrast to that, the other option is isocentric. So they might say, this is an isocentric treatment of, and then they'll continue with the problem. And isocentric relates to SAD, where, you're setting up source to axis or your source to isocenter distance. And then you want to use TMR or TPR or TAR, but typically the common one is TMR. Basically, you just want to know you don't want to use PDD because that is the graph and the associated numbers that physics has generated from the machine, setting up with an SSD setup versus SAD, which you use TMR. So I'll just go ahead and get started. This one, nothing too crazy, but this says calculate the monitor units for 6 MV, 100 cm SSD treatment if the field size is 15 by 15 and the depth is 16. So, field size and depths are important that you would want to know if you were using a chart. In this case, I will say there are some problems I've seen, like practice problems, that they give you a small chart of maybe a screenshot of just 9 different numbers. So 3 going across and 3 going down. And you might have to interpolate in between, a field size if it gives you 14 by 14 and then it jumps straight to 16 by 16. You might need to interpolate and do, if you're searching for 15 by 15, you have to go in between those 2 numbers. Typically it's a whole number, it's not 15 by 15.7. Typically it's not that complicated. They know that, you don't have time to do any crazy calculations, but they do normally like to see that you can do a simple interpolation of just one number. That's probably going to come up on the boards in some way or another. So you just want to know for either searching for your PDD or TMR, you use field size across the top and depth across, down the column. And then continuing with this problem, it says the dose per fraction is 180 centigrade. The SC, which is the collimator scatter, is 1.021, and the SP, which is the phantom scatter or the scatter coming off the patient or the body, is 1.035. The calibration factor is 1 centigrade per MU. And then in this case, it gives you the PDD for your 15 by 15 field size and your depth of 16, and it gives you a TMR for your 15 by 15 and depth of 16. So this would be, one of these answers is probably if you put in the bottom TMR and PDD, which if you kind of know your MU calc formula, that you don't need both of those. So I'll go ahead and kind of write it out, because now that I explained it, it's really not too complicated. Again, because you don't really have to look up graphs for the boards, it's kind of nice in a way. But I know a lot of people say, it's your dose over everything else. But I don't always love saying that, because it's not always on the boards everything else, because they might give you extra information. So on the bottom, I start with like, okay, you're searching for PDD, or I'll put dash TMR in parentheses, because you don't necessarily want both of them. And then times your output factors, which is also your SC and SP. So sometimes they'll just give you like output factor, or sometimes they'll give you both. So I'm just doing this little like caret thing where it's also interchangeable for OF, where it's like output factor, but sometimes they break it up and give you SC and SP. Times I just always put IDL, so that's your isodose line. So like in the problem, if it would say this plan was normalized to 98%, you would want to just put 0.98 for your isodose line, or what you're normalized to in your plan. Sorry, I just want to keep consistent with the times, where I'm just putting these little dots. And then you just have your wedge factor. Another thing that a lot of people always memorize is your tray factor. However, I don't think that they really add that into the boards anymore. I hear that that's something that they probably have taken out. And also it's very simple to just see, like, if you have a block, it'll just say the tray factor is 0.97, and you just know you want to add that in. But the last thing is your calibration factor. I'll just do calibration factor. Okay, so that's pretty much it for MU. So now we can like go ahead and plug it in. The only thing I'll say is you always want to calculate MU per field per fraction. So, if it's saying APPA, if it's saying that the total dose for that fraction is 300 centigrade, you want to divide that by 2, because you know that it's APPA, it's 2 fields. In this case, it's kind of giving it to you nice and easy. The dose per fraction is 180 centigrade, but just always kind of keep those words in your head where you're calculating MU per fraction per field. So I'll go ahead and put 180 centigrade up here on top for the dose. And then in the bottom, we'll put everything else. So starting, we're looking for either a PDD or a TMR. You can see that at the first few words of this problem, it says it's an SSD treatment. So that kind of alerts you right there that you want to use PDD. So in this case, you'll do the 0.65 for PDD instead of the 0.68 for TMR. So you're just not going to put that in at all. And then it gives the SC and SP. Again, on the boards, there's not too many ways to trick you with this part. It's just going to give you either an output factor or the SC and SP. There's probably not going to be a chart that you'd have to find that from. Otherwise, it would be pretty simple. There's no normalization for this problem, so you can just skip the IDL. There's no wedge factor in this problem, so no need to add in a wedge. And then your calibration factor, it says is 1 centigrade per MU, so 1.0, and then I'll just do centigrade per MU, which I always like to just make sure you have something in the bottom that cancels your centigrade and leaves you with MU. So the centigrade down there cancel, the centigrade up there, the dose cancels, and then your unit of MU is going to go to the top since it's in the bottom of this problem. So now you can just simply multiply if you want to just be safe. Like I always like doing, I would do 0.65 times 1.021, just multiplying all the bottom numbers first, times 1.035. No need to multiply by the 1, you'll get the same answer. And then I would just write that number down on your whiteboard. and then do 180 and then divide by that number. So if you're to multiply at the bottom, you get, just write 180 up here. You should get 0.687. And then I'll just put equals here because if you're to do 180 divided by 0.687, you should get 262. Sorry, I know these formulas are long, so I'm running out of room, but your answer would be D for this problem. So does anyone have any questions about that?
So I have a question. In the equation that you wrote out before you put numbers in, it's the scatter, I think it's the scatter factor, SC, is that right? Is that the scatter factor? And then what does SP stand for?
It's the phantom scatter. So like the scatter, it's like they calculated the back scatter that's coming off the patient or the body of the patient. So they say phantom if, you know, they're just calibrating the machine with a phantom that they're using, but it's really like the patient scatter you could put for the P, but it typically stands for phantom.
Okay, so the scatter factor, SC, phantom scatter for SP, and then you have like a bracket and then it says OF. What is OF? Is that output factor?
Correct. Yep, because sometimes they won't give you SC and SP. They'll just say your output factor is, and then it's those two multiplied together. So it'd just be one number, and then you can just multiply that in.
Got it. Okay. All right. And so I have some people that typed some things in the chat. It looks like Mike asked, do we not use the TMR for this problem?
Okay, good question. For this problem, you don't need to use the TMR because it's an SSD treatment. So you know that SSD relates to a non-isocentric setup where you use PDD instead of TMR. But if it would say SAD, because this is where it kind of says SSD up here that alerts you that you want to use PDD. But if it would say S80, that's when you would use your TMR. But this part of the problem is actually extra information where you don't want to use the 0.68 at all for this case.
Ricky. Okay, he says he got it. Great.
Good.
Doesn't look like we have any other questions. So we have time to go through maybe one more.
Yeah, I think that would be a perfect place to stop because I just have one more MU calc problem and it's really not too tricky at all, but it gives a good example with having to solve for the correct dose. So if anyone wants to take a last minute picture of the work here, I will erase this and move on. But this is the other type of MU calc question, which we can kind of just skim through, but you can see that some of the differences are, it says calculate the AP monitor units. So it's asking for you to just calculate it for this AP field. So this is parallel posed APPA, and then it's saying that the total dose is 3,000 centigrade in 10 fractions. So for this, you know, I think probably the biggest mistake that a lot of students do is they'll put 3,000 in the top of this MU question for dose, but you just want to, like I said, make sure you calculate per fraction per field. So then the other thing that I think a lot of people do is they see this 3,000 centigrade in 10 fractions and they say, oh, okay, yes, 300 needs to go on the top for dose. So like whenever you write your MU and you're doing dose at the top, a lot of people want to put like 300 up here. But again, because you're calculating per fraction per field and you know it's APPA, you actually want to divide 300 again in half. So like your if you're calculating just for the AP, it's actually going to be 150 centigrade that goes up here. So definitely stop me if anyone lost me, but if I just write this kind of on the left-hand margin here, if you do 3,000 divided by 10, because that's your total dose, and then in 10 fractions, right, you're going to get an answer of 300. But then because it's APPA, you want to divide the 300 again by 2, and then you get 150 for your AP monitor units that you're solving for.
I have a quick comment
Sure.
or question. But
Yeah.
Kara, would you say it's also something that you commonly would see in clinic? Like, in other words, like if you thought this out in regards to like what maybe you're used to seeing on a day-to-day basis, you know, I don't know if as a student you're familiar with the typical fractionation of a APPA, but you might, next time you have a chart open, maybe it would be beneficial for you to look at the field dose, the amount of centigrade that's contributing with each field, especially on maybe something simple like an APPA, because I think here, if it's the APPA, both components add up to the fractional daily dose. Is that right?
Yep. Yep. If it's just two fields, APPA, they should, the anterior and the posterior, or the two fields should add up to the total dose for that fraction. So they should add up to the 300 centigrade.
Okay, thank you.
Sure, yeah. Okay, then in finishing out this problem, it says treated to the 97% isodose line. So this would be a problem where we use the IDL, where we use 0.97. You never want to multiply something, you know, large like 97%, because that's just going to give you a very crazy answer. That's not close, right? You should be getting an MU that's within like fair range of your dose. So if it's 150, you know, the answers A through D are fairly close or around that. If you would use 97, you would get a very far off answer. And then it says the treatment depth is mid-plane and the patient's separation measures 32. And then it gives you your field size. It tells you that a 15-degree wedge is used in both the fields, and it gives you your reference dose rate, or that's the same thing as your calibration factor. Again, either way, as long as you have something where your centigrade cancels out the centigrade on top and you're left with MU, you know that's correct. And then you have your output factor. So again, I'll just write out the formula just so everyone can see. Let me just go back with that. But you have either your PDD or TMR. You have your, I'll just write output factor in this case, and take out the SC and SP so you can see it written this way, because in this problem, it actually does give you the output factor instead of the SC and SP. Then you have your IDL, you have your wedge factor, then you have your calibration factor. So I'll just do Cal F. But again, you might have a tray factor, but I don't really think it's used anymore. So we'll go ahead and we will finish solving this problem. So 150 centigrade on top for our dose. Now that we're confident that is our per fraction, per field dose for our AP. In this case, it's saying it's an SAD treatment. So we know that we can use TMR instead of PDD. So that's good. You can see from the problem that it doesn't straight out give you your TMR or PDD, but it does give you a little chart at the bottom, which this is something else I've seen on the boards. But again, you're not going to use all these numbers. They give you, if you look at the bottom for the TMRs, it says TMR at a depth of 16, and then it says TMR at a depth of 32. So then you go back to your problem and you see this sentence here that says the treatment depth is mid-plane and the patient separation is 32. So you might say to yourself, I don't see anything with a depth of 16. I'm going to use the TMR at depth of 32. but that's actually the patient's total separation. And you see that the patient's actually treated at mid-plane. So you would divide 32 in half and you would get 16. So you actually want to use this TMR here, where it says TMR at the depth of 16 is 0.83. So I will kind of go and put this at the bottom. Definitely feel free to ask at the end if you're unsure how I got to that TMR using the depth of 16. And then for your output factor, it says it's 0.954. That's the very last part of the problem. That's where I got that. And then the ideal, again, like we kind of talked about, is 0.97 for what the plan is normalized to. The wedge factor in this case, it says a 15-degree wedge is used in both the fields. So you'll want to use the 15-degree wedge factor. You don't need to add it together to get a 30-degree wedge because, again, you calculate monitor units per fraction per field. So you're just dealing with whatever is used for the AP, and you know a 15-degree wedge is used in the AP. So you don't need to use the 30. So 0.98, and then times the calibration factor, or the other word that's commonly used is this reference dose rate, but it's 1.01 centigray per MU. And so again, just to reiterate what I said last time, I would recommend multiplying out the bottom. So 0.83 times 0.954 times 0.97 times 0.98 times 1.01. And then I would get that answer, which if you multiply out, you should get 150 centigray. On the bottom, you should get 0.76, or at least something close to that is what I got. Sorry, this is not super clear, but this is 0.76. And then finally, if you do 150 divided by 0.76, you should get 197, which is B. So definitely, if anyone has any questions on that, feel free to ask. But otherwise, that's all I really have for MU Calcs and some of the different ways in which it could be asked.
Okay, so does anybody want to ask Kara before we can spend another 5-10 minutes just going over it, because I feel like, and Kara, I mean, correct me if I'm wrong, are you able to stay on for, you know, another 5-10 minutes before? I mean,
Yeah,
that way,
definitely.
I think we really want to see that you guys feel like you're tracking, and it's understandable if you're not tracking, especially if this is the first experience that you've had with MU calculations. A little background from my understanding, and Kara can correct me, is that when someone is calculating monitor units, you know, a therapist might be asked to do this. Of course, these days with the help of a software program and a calculator that will already have, you know, your facilities, output factors, scatter factors, like it'll all be programmed in there based on like field size, patient, whatever. But it also has, you know, calibration factor. But, you know, a therapist may be asked to deliver, you know, something to relieve pain. You know, there could be a cord compression, or it could be a superior vena cava syndrome, and it may require, you know, measuring the thickness of the patient, delivering a mid-plane treatment, both in the AP and the PA, to, it could be 300 centigray, it could be 500 centigray, but regardless of what the doctor is asking for, the premise in this example is you're only dealing with it per field for one fraction. So when you're asked for the monitor unit calculation of one field, you know, if for instance, in this example, the one fraction will be receiving 300 centigrade, but because there's two components, there's two fields, you need to break that into the two component parts. 150 contributes from the top and 150 contributes from the bottom. And all the other factors that we're using to divide by are things that will attenuate the beam, so that they require, pretend like the beam's coming from below the patient. What's between the patient and the beam is the table. And so, that's the way I think about it. It's like I'm very concrete. I'll think, okay, well, there's some factors that need to be taken into account to if nothing else, at least the table, because, the table will attenuate the beam. So when I think about my answer, I think that the answer needs to be more than the amount of centigrade that we're delivering inside of the patient, because when you're shooting the monitor units, they're coming from the machine, penetrating the table in which they're being attenuated, and then being delivered at some thickness inside of the patient. And all that requires maybe a little extra oomph to pass through all those things, to attenuate all the, through the distance, but still deliver a point dose of 150 centigrade. And I hope I didn't get too far into the weeds, but I want to give some context of why in the world do we see all these numbers in the denominator. And basically, they're just all these little factors that can attenuate the beam. And therefore, our monitor units need to be, most often, I've never seen it any other way, our monitor units need to be greater than the centigrade dose that we're solving for, that we're trying to calculate monitor units for. Would you add anything to that, Kara, or did I miss something, or did I misspeak?
No, I think that is great. 100%. I'm on board and agree with what you say. The only thing I will say that is something that I learned from doing this over and over, that maybe whenever you get an MU calc problem that you could keep in mind, is the lower that the numbers are in the denominator or the bottom, the higher your MU, your final answer of MU should be. So like, for example, a 15-degree wedge, you have a number of 0.98, meaning it doesn't really attenuate too much of the beam, but exactly like Lauren said, something's in the path of that beam, so you need a little bit like extra to pass through that. But if you would see a 60-degree wedge, your number is going to be like 0.7 or something like that. And that's really going to amp up your MU. So, you can see you have, because a depth of 16 centimeters is pretty deep into the patient. That's why your PDD is pretty low. It's only at 83% of 100% of that dose. So that kind of helped really amp up this MU calc number, where it went up from 150 from the dose, like Lauren was saying, to 197. That this number really helped amp that number up. So that's something I would say on the boards, is if you're seeing, the bottom numbers being like 0.9, 0.97, 0.98, 1.01, like those are all very close to 1. You're going to get a number pretty close to 150. So if you don't, you probably made a mistake in your calculator. But if you have really like low numbers, like 0.6, 0.7, 0.5, you're going to get a very large MU calc answer, and that's correct. It's nothing to be alarmed with. I feel like a lot of students I've helped are like, this MU is double, like I did something wrong, it's not right. And I'll be like, but look, you have like a 60-degree wedge in that field. So of course you really have to amp up your MU in order to deliver the same dose to that isocenter or that point. So it's okay. So that's just something that I would add to what Lauren was saying, that you can kind of use as a helpful trick to know that you got the right answer or close to the right answer on the boards, if that made that made sense to anyone, but definitely ask questions if that was confusing.
All right, would anyone like to be unmuted and talk with Kara directly about this problem before we move on? You could say me in the chat, or you could type your question in the chat. No, okay, no one's in the chat. And okay, so Kara, we were able to get through 2 monitor unit calculations, and I think the only thing we did not get through was wedge and hinge angles and average life. Is that something maybe you and I can go over privately, and I can share it in a video with the students?
Yeah, no, definitely.
Just Logan, let's see, what does he have? Logan says, I think you really simplified it. Thank you. The questions can be very intimidating. Yes, I agree.
Yep.
Okay. So we want to make sure, being confident with calculations, the whole purpose of this 2-part series with Kara is really about helping you guys feel more comfortable navigating these intimidating questions. And so if you feel intimidated, that's okay, because you're not alone. And I'm going to be continuing to produce content through the newsletter, through more of these Thursday sessions, to help break this down, to help go over this again, to be able to maybe work through more problems together. You can check out my YouTube channel. It's Radiation Therapy Zone. I've already got 1 video posted from last week, and I'll be posting tonight's video this weekend. Does anyone have anything they want to comment or any questions before we wrap up? One thing, while you guys are typing or thinking, one thing I would ask you is, if something is on your mind, maybe jot it down on a piece of paper and just send me an email, reply to one of my emails, and ask me via email. If it takes a little longer to type up, or you just need time to think about it, it's completely understandable. If you tell me where you're struggling or what topic concerns you, we can spend more time on it, and it may help direct where I spend a lot of my time and energy going forward. So just wanted to ask you guys to give some feedback in that way. All right, well, we don't have anything going on in the chat, so we're going to wrap up. Here, is there anything that you want to say to kind of leave with the students? And you gave us a lot of great advice. I mean, you're just real, you told us, not to be too worried if our denominators are very small numbers, because it would give us a large result in the monitor units. You shared with us how to break down logical steps and kind of evaluating how we've arrived at certain answers to kind of pick the best of both. You've helped us kind of pinpoint, focusing on, having the right, looking at the right item that we need that's relevant to the question in whatever chart that could be provided to us. Whether that's interpolating or whether that's looking at the mid-plane depth as opposed to the complete separation of the patient, and looking at the appropriate TMR factor for that. But do you have anything generally, whether it comes to when is the best time to schedule your exam, or when is any tips on how do I prepare the night before, the day before the exam? Anything you'd like to leave the students with?
Yeah, the only few things that come to mind that I normally tell students is to, on this subject, have your formulas all written down in a sheet, so that you don't have to be worried and keep them all in your head. You can just have them all out in front of you, visually see them, kind of go through it the night before or the morning of, and be like, activity. I know I can picture the type of question that I know I'm going to need to use the activity formula for. I should be given a time, I should be given a half-life, I should be given an initial activity. And like, if you just go through each formula and you say, I know what a question that I need to use this formula looks like, that's something that could really help. And if not, you know, you could search out those problems and figure it out in your textbooks or something like that. But other than that, I always say, you know, the typical things, get plenty of sleep, you know, make sure you have everything compiled the night before, whatever you're going to take to the test, your ID, you know, everything. Drink lots of water, schedule your test at the time that you think the best. So if it's in the morning, if it's in the afternoon, do that. And I always tell people, because they always say like, how do I know when I'm ready? I usually say, unless you're very busy at that point in your life for some reason, that might be unexpected, the closest to when you graduate is probably the most beneficial. Within like a few weeks or a month, that's definitely not unreasonable to take a few weeks off and just devote to studying. But whenever you start to move out like months or years, that's typically where it gets a lot harder to remember things. But I would say if you do a lot of practice tests, I feel like that's a lot of things that students use these days, is like the Mosby's online practice tests, the ASRT questions. I think there's a few different platforms. If you start to, you know, take tests, whether it's 200 questions, you know, 100 questions, 50 questions, doesn't matter. And you start to calculate your percentage, right? You should just be getting over what a passing score is. But I always try to like amp it up like a good 5 to 10%. So I know for me, whenever I was preparing, I was aiming for at least 75 to 80 in order to just give a little bit of leeway, you know, in case the questions happen to be harder on the boards than what I just happened to be studying. But once you start to score over passing scores, you're probably ready to schedule your test and feel confident about taking it.
Okay, great. Thank you. Good advice. So that's going to be happening in the next probably 5 to 6 months for a lot of you guys. In the meantime, check your emails. I'll be emailing every Thursday, coordinating more of these Thursday tutoring sessions. We will, you know, it'll be myself and you guys. It'll be more kind of personalized. And so we're going to take a break on these tutoring sessions. So for the next 2 weeks, you'll just be getting value-packed emails where I'll be talking about really tips on study tips, especially for taking like standardized tests. The next one specifically, I want to go through what a good cheat sheet, like a exam prep calculation cheat sheet might contain, and helping you guys develop your own exam prep cheat sheet, like Karen mentioned. Having that at the ready and doing that earlier in the game helps you really internalize a lot of these equations, because you're familiar. Every time you do a calculation, you bring out your cheat sheet and you know, oh yeah, my activity is located in this little section here, and I can imagine where it is on the page. And anyway, so that's the next topic for next week. And so for the next 2 weeks, so through Christmas, we'll be doing emails. Check your emails, and then we'll be following back up with Thursday after New Year's with another tutoring session. So love to see you guys join in for another tutoring session. And before we go, I just want to make sure I share with you, if this is your first time joining us, or maybe someone shared a link with you and you didn't sign up on my newsletter page on my website, please visit laurenjbrown.com and make sure you sign up on that page, because that's how you're going to get future emails from me. So I understand if you want to share this with a friend, fantastic, please do. you can just forward the emails on to your friend, but if they're interested in getting more emails, make sure they actually subscribe to the newsletter at laurenjbrown.com. Also, I'll send a link with the calculation, going through a calculator with the log for activity, because I think that'll be helpful. A little screenshot, probably be like 5 minutes or less. And I'll post that on YouTube. And I'll also send an email with a link to the first video as well as the second video for tonight's session. So you guys will have, feel free to review that. There might be some things that can, you may benefit from going over again and just hitting replay and repeat to kind of hear what Kara was mentioning. Maybe walk through the problems one more time with Kara. Also, to Olivia's question, I'd like you guys to go ahead and complete the practice problems that maybe you didn't complete because we only went through the second half today. Go through those on your own, and I'll email you guys the key so you can compare your results, and then we can also maybe our first time back, we can go through those results. So on the Thursday after New Year's, we can go through those results, go through any kind of places you may have gotten stuck, and might be a good way to start things off. Thank you guys for joining us on our series for Confidence with Calculations.